So hi, my name is Lian, and I'm called Vice by Professor Phan Protege. And before I start my presentation, I want to thank Niraj for the guidance and also Professor Phan for the guidance. And also I want to thank Ifan for the assistance over my thesis. So my thesis project topic is online rotor fault detection and isolation for the vertical takeoff and landing vehicles. Um, so let me first introduce why we want to do this research. It is basically because there's increasing popularities of commercial eVTOLs. There's pioneers companies here, Joby, Archer, and Lian, and the study has shown that the usage of eVTOLs has reduced the congestion and also possible to save your time in commuting, which is up to 30% of time. However, the problem is the rotor can fail and can cause crash. We have two examples. They are both military ones because commercial eVTOLs just counts. The left one is F-35B and the right one is MV-22. Both happens when it is landing. So this problem is critical, and the previous solution is people can use engineers can use high precision sensors, but we do know in the companies there's discussion that the sensors are too expensive. So our goal is why not we change another way. We do the fault detection and isolation software. For example, use the post arrow. There's challenge also a lot of challenges. The first one is current FDI techniques mainly focused on the fixed wings and modular system. So only a few studies works on the hybrid system like VTOL system. And also the rotor force can max by the ailerons. There's only a short time window before the rotor force are maxed. Here we provide an example of when 10% fault injected rotor 2 of our vehicle, you can see it is quickly maxed by the aileron, and it only takes 3 seconds to converge from the turbulence. So after it has been maxed, there's no way for us to detect the faults or from the post arrow. However, you may think the masking may be safe and also allow the vehicle to be operationally safety, but masking doesn't extend to the vertical flights. Yeah. And the rotor force happens. So we target this condition that the rotor force happens in the cruise flights, like the states here, and then the fault is maxed in the seconds. So you can see there's no way for us to see whether the fault is here from the 3D trajectory. However, the hidden fault can cause crash while cells both reaching and landing. The GIF image just shows this condition. When the landing command activated, even though it is stably flights, however, when the landing command activated, the ailerons cannot mask the fault anymore, and it just crashed. So we already introduced why we want to do this research. How about we go through the model we use for the experiments? At first, we want to build our VTOL system, which is similar to the popular commercial eVTOLs like Joby passenger eVTOLs. However, we didn't have the access to it, so we modified the existing VTOL system like Delta Quad plane, which provided by PX4 system. So we add 2 ailerons on the wings, and you can see here. Then there are 6 rotors and 2 ailerons, and we also disables the pusher rotor on the back. And finally, we have the actuator indexing map on the right for you to review for the reference, of course. And just an overview of our methods. It basically comprised of composite have two composition, and the first one is the fault detection. It means we want to determine the existence of the fault to see whether the fault is here. And the second part is the fault isolation. We already know the fault is here. We want to shrink the candidate list maybe from 6 to 3, and finally to 2 and 1. And it helps us to identify the specific faulty rotor. And afterwards, we already know which rotor is fault. We compute severity level of the faults. When we say severity level, it means the content of the faults. If the rotor lose 10% of the total faults, it means it has 10% of severity level. And for the detailed step of the fault detection, we first do a step called data gathering. We have two buffers. One is baseline buffer, delta B, and one is post-error buffer. Baseline buffer just collect the initial baseline data before the first fault is detected. It is the post-error information during the stable cruise flights. And we calculate the standard deviation of the data as reference, and we also use the median for the adjustment afterwards. And for the post-error buffer data N, we use it to do the continuous monitor the flight status. It also records the post-error information. It just keep flashing and accepting data from the internal buffer. And the second step, we call it thresholding. We compare the difference in the error medians recorded over both buffer to the weighted value of standard deviation computed in the baseline buffer. So we have provided you the two equations to show our logics. The first one measured the condition that both row arrow and pitch arrow reach the thresholds, and the second one measures the condition that either one of the type of the arrow reach the thresholds, and both conditions just will trigger the flag that the fault has exists. And after we do the FDIR steps, the fault detection, isolation, and finally recovery, we will recollect the baseline buffer to adapt sequential faults. For our steps of fault isolation, we want to shrink our candidate list. So the first step we do is we isolate the half space. We define two half space for this video model. The first one is half space 1, which contains rotor 1, 3, 5, and the second is half space 2. It contains rotor 2, 4, 6. And we analyze the sign of row and pitch arrow overshoot immediately after the detection of a fault. And you can see this is the first overshoot after the detection of faults. The green background means there's no faults, and the red background means there's faulting has been injected. And we check the sign of the overshoots, they are both positive. And we check with the inference table for the row arrow and pitch arrow. We see it fits the condition of second row, so we can state that this fault comes from the half space 2. And afterwards, we want to further shrink our candidates from 3 to 1. So we identify the faulty rotor. We compute the error ratio from the peaks of row and pitch arrows stored in the delta M buffer. It is also the overshoots here, and we just divided some and got the error ratio to be 0.6. And we check with the pre-recorded error profiles provided here. These are gathered from our experiments, and you can see the error profile is very similar from both of the half space. So in for the rotor 1 and rotor 2, it concentrates around 0.6 and 0.7. And for rotor 3 and rotor 4, it concentrates around 1.2. And for Rotor 5 and Rotor 6, it has larger variation, and also it concentrates around 2.2. So there's no much overlay between these rotors in each half space. So we can, as we got the error ratio that is 0.6, we can, and we know it is come from half space 2. So we can say the faulty rotor index is 2. And finally, in the last step of fault isolation, we want to estimate the severity level. We already know the which rotor is false, so we just want to utilize the peak aileron control signals after fault injection to do this. The red block just show you where is the peak aileron control signal. And the green box is the one which already bounded. When the bounded peak aileron control signals happens, it means the aileron can no more max the force and will cause crash in the future flights. And we repeat the experiments of 1% to 30% for each rotor. And we got the diagram on the right-hand side. And after that, we just estimate severity level as the quadratic function of eta A. So basically, when we know the fault rotor is number 2, so we apply it to the second diagram, and we just use the eta A we have and multiply with the coefficient we got from the diagram. And the last step of this method is recovery. As this is not our key steps of the research, we just use the very simple recovery implementation to verify our methods. So if the estimated severity level is determined S dot approximately equals to the ground truth severity level, the updated rotor input becomes a minimum of Ti, the current inputs, divided by 1 minus S dot, compared with the maximum inputs. And to better show you how we do the experiments, I want to show you the simulation platform and how it works. It is basically built on the PX4 simulation stack. We use the Linux terminal to do the basic command control, and it is rendered in the conceivable environments for the visualization and the physical simulator. And the Q-ground control just used for the flight planning and telemetry monitoring. And also we want to mimic the real world environment, so we inject random winds from 0 to 2.5 meters per second as noise. And before we evaluate the results, I want to propose 3 questions for myself to answer. The first one is, how accurately can our technique identify the faulty rotor and severity? The second one is, once the fault is isolated, how effective is our method in enabling even simple recovery techniques to allow the system to land safely? And the third one is, how quickly can it isolate a faulty rotor? To answer the first 2 questions, for the accuracy and safety preservation, we have defined 2 parameters. The first one is FDI accuracy, and the second one is landing success rates. And for the FDI accuracy, when we say a case is accurate, we mean it can estimate the fault severity to within 2%. And the diagram on the left has shown that for one severity level, we only have like 70% of FDI accuracy. It is cool, at least for me, but 100% of landing success rate is observed because 1% severity level doesn't harm the flight safety at all, so it doesn't matter. So based on that, our overall FDI accuracy is good, which is over 91.67%. And for the landing success rates, we not surprisingly, because 1% and 3% doesn't harm the flight safety, so it is 100% for both the case. And for the severity level increase from 5% to 25%, it increased from the landing success rate also increased from 91.93% to almost 100%. And to dive further into this accuracy question, let me show you the estimation gap of the severity levels we have collected from the experiments. This diagram just summarizes the estimation gap statistics of the case which successfully detect the faults. It doesn't include the situation that our algorithm doesn't able to detect the faults. So from the diagram, the median of all severity level is all around 1%, which seems to be good, and only outliers in 25 severity level reach the 2% estimation gap. And we can state that if the fault detection is successful, our fault isolation is almost 100% accurate. And just be notes, it doesn't have consider the situation like for the 1% severity level, the fault may be very low, that it is immersed by the noise. So and our algorithm cannot like drag the how to say our algorithm may not be able to detect the faults. And to answer the third question, here is our runtime performance. This diagram on the left, the y-axis means the time spent in seconds from the time the fault has been injected, which is the ground truth time of the fault existence, to the time we finish our FDIR process. And our FDI algorithms takes longer in low severity level especially for the 1% severity level, but we see substantial improvements in the speed of FDI, even from 1% to 3% severity levels. And for the severity levels greater than 3%, the FDI remains near constant around 2.3 seconds. And finally, I want to show you a video to better visualize our algorithm's performance. It is the comparison of it is just a comparison between the vehicles with the FDIR algorithms we developed and the one without. And now when it takes off, the baseline buffer just keeps running, and the post-error buffer runs to monitor the flight safety. And 10% fault has been injected to rotor 2, and you can see both vehicles just turbulence, and then both are maxed by the ailerons. Now there's no difference between the two vehicles. However, one doesn't have FDIR, the fault is still here, but another one with FDIR, so it has been processed, the fault has been covered. And when the landing command activated, so one without FDIR just crashes and lose control, but the one with FDIR just gradually landing and finally successfully land to the ground. Please. And just to summarize my 2 semester thesis, we face the problem that the FIDO rotor can fail and cause crashes, and the force in FIDO is maxed by the ailerons. So we proposed the solution, which is the new FDI method, use post-error and aileron control signal to quickly detect and isolate the faults. And overall, its performance is good. It is able to deal with the fault within 2.3 seconds. It also achieves the FDI accuracy higher than 91.67%, and it improved the landing success rates to 91.93%. And although it is good, we still have a lot of future works to do. The first thing is our work is still in the steps of simulation. We still need to make the physical model to verify our method. And the second one is our method lives with the overfits to the ideal simulation environments. Even though we already have the noise as random winds injected to the simulation, but it is not enough. The real world is more than that. When we change the fetal model or we change another simulation controller configuration, we probably need to change the parameters of our FDIR algorithm. So in the future, we may need to explore a more robust method to deal with that. Thank you for your listening.
Questions? So you're assuming a very specific type of fault, right? So do you actually, when you say that it's actually isolated, do you like not use the rotor that you detected as faulty, or do you sort of max out the rotor that is faulty? I wasn't quite sure what that.
Sorry.
So one of your rotors, you detected that it's kind of not functioning, right?
Yeah.
Particularly well. So then do you not use it, or do you sort of max out the function, sort of?
Yeah. We just max when we know which rotor is faulty, we just for example, it is 90 it can only output 90% of the fault. We just maximize to maybe 1.1 110% of the fault it proposed to false.
Okay, so you're basically trying to compensate for the loss.
Yeah, we just do compensate the fault.
Okay. And so, but it's not, okay, so then the other question that I have is that, when you detect this fault, right, you're kind of assuming that, it's a binary thing. It's detected and therefore the rotor is faulty, right?
Yeah.
But do you keep monitoring to see if the rotor like recovers on its own?
Actually, no. But we do collect the baseline buffer again. So we know we have considered this part as a part of noise if it is not inaccurate.
Yeah.
And if it is so inaccurate that it can harm the flight safety, we do consider it as the fault and estimate again.
Other questions?
So could you please go to the page 18? 18. Yeah. So when you mention your runtime performance, the low severity level takes more time. Could you just please expand the reason?
Actually, it is because in the previous step for the fault detection, and it is the equation here. We actually use the error medians. When we use the error medians, for the low severity level, it just takes longer for the buffer to have a medium that reach the threshold. So it takes longer. However, for the one without for the one with larger severity level, it just takes shorter for the mediums to reach to the threshold value.
So one more, anybody? Go ahead, Ben.
Yeah, in the case of a multi-rotor failure,
Uh,
Would the
yeah.
procedure still be the same? Because I would assume your method of isolation would be different.
It is supposed to be the same, like because we have updated the baseline buffer, so the baseline, the reference is the same. The reference may be different, though we make the ground to be different, and so the threshold is different. It is still the same. Compared with the reference.
Maybe we will differentiate between sequential versus concurrent. So I think what you're talking about is one called after another, and he's asking about what are two things happening at the same time.
We
The
haven't.
difference is you would have a different threshold.
Yeah, we now we haven't considered the case of the two fault happens in the same time. We just consider there's one fault comes and maybe after sometimes another fault comes.
So last question, because I'm super curious. When you did the random, right, you did random when, but you did it in terms of random in magnitude, did you change was it also random in direction as well?
Yeah, it is actually this default setting of the PX4. We can change the wind speed, and it is assumed to be like random direction, but it do have some training embedded in the system.
I'm just curious because, you know, how the wind speed, the relative wind direction, right, in relation to the heading of the vehicle may also be more, you know, have a more significant or less significant impact on the different rotors within the system, right? So that would be, you know, another interesting. Other questions?
One small question. So for your PS4 simulation, so is that dimensionless? For example, if your aircraft is super large or super small, your resource be different. So
Okay.
yeah, in your PS4 platform, so what's the size of your aircraft, your vehicle? If your vehicle is super large, super small, well, you're different. Well, your outcome be different.
It is a good question actually. Now we only have one model. We haven't tested for other models, but we are sure that I'm sure that if we maybe make the model to be smaller, the wings impacts our noise maybe becomes larger for the flights, so the pulse arrow would be a difference. And also in our future work, I have mentioned that when the model have been changed, the parameters of our FDI algorithms is highly possible to change. So we do consider it as a question for our future work.
Okay. Any last questions? Let's thank first speaker.